Thank you all very much for coming to this session today, sparing your very, very busy schedule. And participants from online, thank you also very much for joining this session. We would like to now begin the 16th Symposium of the JAEA activities. I will be the moderator for this session today. I am from JAEA, Fast Reactor and New Reactor Research and Development Department, Yoko Akutsu. So nice to see you all today. There will be 20 minutes of break time, and it's going to continue till 4:30. With that, on behalf of the organizer, I would like to call upon the president of JAEA, Mr. Toshio Kodama, to give us the opening remarks, as well as the keynote speech titled Challenges of JAEA Towards Fourth Medium to Long-Term Objectives, period. Good afternoon, everyone. I am Kodama, President of the Japan Atomic Energy Agency, JAEA. Thank you very much for taking time out of your very busy schedule to participate in the 16th Annual Symposium of the JAEA activities. This year's symposium is an hybrid event with live and online. I would like to express my gratitude to all of you for your kind participation, and I hope that this will be an opportunity for you to learn more about our activities. The other day, the 6th Basic Energy Plan was approved by the Cabinet. In addition, at the 26th Conference of the Parties to the United Nations Framework Convention on Climate Change, COP26, Japan expressed its strong determination to play a leadership role in decarbonization. And the world is accelerating its efforts towards decarbonization in order to establish a sustainable society. Being attentive to what's happening both at home and abroad, JAEA has chosen the theme of To the Future, Sustainable Future with Shin Nuclear Power as the theme of this session. We will begin with an introduction of JAEA's efforts in the 5th Medium to Long-Term Challenges, and will explain our activities of the 4th Medium to Long-Term Objectives period starting next April. Next, Dr. Oshima, Director of JAEA, will introduce JAEA's R&D efforts to contribute to the realization of Japan's goal of carbon neutrality in 2050 under the title of Nuclear Innovation for Carbon Neutrality. After that, there will be 3 topics on advanced research and development will be introduced by our young researchers and engineers. I hope you will be able to see some of the R&D and technological developments we're working on. In the latter part of the session, we will have a talk session with experts on the possibilities of new nuclear energy that JA is aiming for, called Shin Nuclear Energy. I hope that this will discuss the possibilities of using nuclear energy in various fields, not limited to energy use, but also the expectations for nuclear energy. In closing, I hope that today's briefing will help you to learn more about the activities of JAEA and deepen communication with you in the future. Now with that, I would like to introduce the challenges that JA is facing. Thank you very much. I would like to now introduce the challenges of JAEA in the 4th medium to long-term period, which is the 7-year period from next April to March 2029. In my presentation, I will describe the direction of the challenge. Please listen to the presentation after mine for details of specific examples of the contents. I will also have experts discuss the challenges from the perspective of the new nuclear Shin atomic energy in the talk session in the second half. Shin atomic energy is an initiative to actively promote R&D and technology development using radiation and electromagnetic waves, in addition to R&D related to conventional energy use, which is the first and foremost area of our R&D. It is also an initiative to actively promote open innovation, industry-academia collaboration, and other collaborations outside of JEA. In the next 7 years, which is the next medium to long-term period, JEA will take on the challenge of creating innovation while balancing R&D with the decommissioning of facilities. On these, in today's presentation, I would like to particularly introduce the challenge to create innovation. Here is the table of contents. After describing the changes in the social situation surrounding nuclear energy and the role that JEA should play in light of these changes, I would like to introduce JEA's challenges for the fourth medium to long-term period, including our policies, examples of initiatives in each field, and our methodology or how to do for creating innovation. First, the social situation surrounding nuclear power. As shown in the upper block, efforts to achieve carbon neutrality are now accelerating on a global scale. In addition, the creation of scientific and technological innovations for the realization of Society 5.0, the future society, has become indispensable. If you look at the lower block, under these circumstances surrounding atomic energy, innovation in the technology of energy is expected as it's the decarbonized power source toward carbon neutrality, and innovation creation that leads to the solution of social issues is also expected. Based on the above, the role of JEA for the sustainable use of nuclear energy is to conduct research and development of such energy, which is essential for carbon neutrality, and to build a technology and knowledge-based platform. To engage in innovation creation activities that will ultimately deliver the results to industry. To promote international collaboration for R&D, for advanced atomic technologies and utilization of its platforms. I believe that decommissioning of the facilities should be carried out safely and steadily while balancing R&D activities. To this end, as shown in the block on the right, we will put into practice the future vision JEA 2050+, which was announced the year before last, and promote cross-organizational and strategic promotion of R&D towards the positioning of new atomic energy as our new approach. As I mentioned at the beginning, Shin nuclear atomic energy is an initiative to actively promote R&D and technological development using radiation and electromagnetic waves, in addition to conventional R&D related to the energy business, and to actively promote collaboration with outside JEA. Next, I would like to talk about the policy for the next medium to long-term objectives period from next April to March 2029. As shown in the upper blue block, in the next objectives period, We will aim to promote both R&D activities and decommissioning activities while fulfilling our social commitments and securing management resources as our top priorities for safety assurance operations. In the block on the left, we will move towards with efforts to break away from self-reliance in R&D activities to improve our strength and strengthen our weaknesses to actively support private R&D activities. As for decommissioning, we will promote a three-pronged plan to consolidate and focus R&D functions, ensure safety, and take measures for the back end and develop technology necessary for waste. This page is regarding the strategy for the creation of innovation. As shown in the blue graph in the upper part of this page, based on the revised version of the innovation creation strategy formulated last year, we will strengthen our open innovation initiatives to promote technology transfer and bridging to the sector, strengthen social implementation, manage innovation activities, and enhance R&D capabilities. In the yellow box, the revised strategy clarifies the strategy based on the strength and weaknesses of JAEA in order to realize the new nuclear energy. The strengths of JAEA are, as you can see under the blue marker, the fact that we have test reactors and hot test facilities, as well as wide range of knowledge and technology related to atomic energy. On the other hand, the weaknesses of JAEA are listed under the gray section, such as the lack of open innovation initiatives and organization-to-organization collaboration with external entities. We will try to resolve these issues in the future. From this page, we will introduce examples of our efforts in each field towards positioning the new atomic energy. In addition to the conventional fields related to energy utilization, we will actively promote the application of our achievements in various fields other than energy and actively challenge new way of atomic energy initiatives and bridge them to industries. Examples include the development of low-cost, high-performance metal absorption technology using waste pork bones, which has been featured in newspapers and on TV, and the development of a simple, low-cost, high-performance rare metal recovery method through the establishment of JAEA-launched venture, which I will introduce later. These are just a few examples. This page shows the challenge to strengthen the basic research capability to support nuclear energy. In this block on the left, we will promote fundamental R&D to contribute to the sustainable use of atomic energy and the transformation of society in the future by making the best use of the knowledge base that JAEA possesses. In the block on the right, we will create innovations in a variety of fields using neutron beams, etc., utilizing the features of the JRR3 test and research reactor and the JPARC high-intensity proton accelerator, respectively. This page is about the decommissioning of the Fukushima Daiichi nuclear power plant, the so-called 1F, and the challenge to restore the environment. In the upper blue block, we will promote decommissioning of 1F and environmental recovery by demonstrating the comprehensive R&D capabilities of JAEA. We will also utilize the knowledge gains in this process for decommissioning of JAEA facilities.
Specifically, as you see on the upper left box, we will conduct research on analysis and evaluation of fuel debris and radioactive waste in accordance with mid to long-term roadmap of Japan. As you can see on the left bottom block, We will steadily conduct environmental recovery-related R&D, which meets the needs of local municipalities in line with the basic policy on reconstruction of Fukushima. In the box on the right, we will prepare and enhance basic research infrastructure necessary for R&D. This page is on the challenge to establish innovative nuclear reactor system. Upper blue box, please. To steadily promote R&D for fast reactor cycle, SMR, Htgr hydrogen production in line with green growth strategy and basic plan on energy, in cooperation with government and industries. Specifically, as you can see in bold letters, we will continue with the initiative for nuclear innovation called NEGZIP, launched by Ministry of Education, Culture, Sports, Science and Technology and Ministry of Economy, Trade and Industry. Initiatives to contribute to fast reactor development, such as creating database by using knowledge and experience gained through Jaea and Monshu. Moving to the right-hand side, in the area of Htgr to contribute to carbon neutral, we will promote hydrogen production and enhancing technological foundation by using Htgr, which restarted its operation in July. In the area of irradiation test and development of fuel materials, we also promote activities to restart experimental fast reactor Jaea to achieve innovation in production of RI for medical use. This page talks about challenge to establish nuclear fuel cycle. Upper left. First, promote R&D to improve reliability of waste disposal using underground research facilities. Lower left. Enhance support organizations to meet the needs of electric power companies and Japan Nuclear Fuel Limited and promote R&D for LWR, reprocessing and fuel production technologies and strengthen human resource support. Upper right. Combining computational science and elemental technology developments to promote R&D on trans-uranium and disposal of nuclear waste technology. Lower right, please. Capitalize on Jaea as test field, promote technological development of nuclear fuel cycle in line with the development of new type of reactor to meet the demands of society. This page is on the challenge to strengthen nuclear non-proliferation and nuclear security. Upper blue box. In order to build a safe and secure society free from threat of nuclear proliferation and terrorism, promote R&D which meets the challenges of nuclear non-proliferation and nuclear security while securing international cooperation. Specifically, as written in bold letters, we will promote nuclear non-proliferation, sophistication of nuclear security technology, support policy making, capacity building of human resources both at home and abroad, support international verification system based upon CTBT. This page is on challenges to back-end measures. First, upper blue box. To establish a streamlined project management structure and technical framework focusing towards fifth mid to long-term objective period, where decommissioning and nuclear waste business should start full-scale operation. In specific, as written in bold letters, proper establishment and enhancement of project management of decommissioning, innovation for decommissioning reform, establishing standard and technologies necessary for waste package used for repository, promotion of disposal business. By promoting these, we would like to steadily proceed with back-end measures. From here, I will introduce methodology, how to do. First of all, the strengthening of open innovation measures. Open Facility Platform is to offer JAEA's facilities, equipment, and devices to people outside for their use. This is the efforts to engage in R&D to find seeds for innovation in collaboration with external partners. By using Open Facility Platform, which started its operation this year, in order to contribute to create innovation through an all-Japan efforts, we will promote the usage of our facilities, equipment, device, taking a restart of JRR3 as a good opportunity. We will set up single contact point to offer one-stop services to make it easier for outside partners to use. This page is on management of innovation activities. Upper blue box, please. For the purpose of overseeing innovation activities of JAEA, JAEA Innovation Hub was established in October this year. We have invited people from outside of JAEA to serve as the head of the hub and senior advisor. A section on the left, in line with a basic policy for creating innovations, as you can see in the light blue area in the middle, 5 sections are set up to address each topic. Led by this organization, JAEA's initiatives for creating innovation will further gain speed. This page is about utilization of intellectual property within the concept of enhancing social implementation. Box in the bottom on the left, out of patents JAEA owns, we have identified promising technologies with high potential of commercialization in areas other than nuclear. We have published technical theses to describe these technologies. Some of these technologies are highlighted in intellectual property infographics to make it more friendly. We also made video featuring animations to encourage a social implementation. These videos are available on JAEA's website. I hope you will enjoy watching them. This page is about venture business creation in the context of enhancing social implementation. Upper blue box. JAEA have approved JAEA-originated venture business called Emulsion Flow Technology, EFT, in June this year. As you can see on the upper left-hand side box, this is to use R&D activities of JAEA to solve social issue, shortage of rare metal, by recover rare metal from urban mine. This is to use new solvent extraction technology, emulsion flow, to conduct high-level separation of elements contained in spent fuel. As you can see in the bottom right-hand side box, we aim to become de facto standard in rare metal recycling business and total support business. This is the last page. This is the executive summary of my presentation. In order to achieve JAEA's mission of contributing to welfare and prosperity of human society through nuclear science and technology, while capturing the demands of the times, we will continue to take on challenges to achieve next mid to long-term objectives. I would like to ask your continued support and understanding. Thank you for your attention. Thank you, President Kodama. We have many distinguished guests in attendance today. Due to the interest of time, allow me to introduce only members of the Diet. Member of the House of Councillors, Mr. Ijima Kiyoshi. Member of the House of Representatives, Mr. Ishikawa Akimasa. Member of the House of Representatives, Mr. Fukushima Nobuyuki. Thank you very much for taking time out of your busy schedule to attend this symposium today. We have also received many congratulatory telegrams today. Member of the House of Councillors, Mr. Miura Nobuhiro. Member of the House of Representatives, Ms. Omi Asako. Thank you. We now like to move on to the presentation of Jaea's research results. Today's presentation materials are available on our website. For those who have questions for today's speech and presentations, if you are participating online, please send your questions to the address which we have informed you at the time of application. A video recording of today's symposium will be posted on our website.
Now we would like to move on to the presentations. The first presentation would be under the title of Nuclear Energy Innovation Towards Carbon Neutrality, and the director of JAEA, Mr. Oshima, would take the floor. My name is Oshima, director of JAEA. I would like to make a presentation on nuclear innovation toward carbon neutrality. First of all, I would like to talk about the current status of energy in Japan, the government's policy and actions regarding carbon-neutral atomic energy, and the development of Shin atomic innovations that JAEA is promoting. In particular, I would like to talk about the developments related to high-temperature gas cooling reactors and fast-cycle technology. First, let me talk about the current status of energy in Japan. Japan's energy self-sufficiency rate is about 12%. As you know, this is quite low even among developed countries. And this means that we depend on energy from overseas for almost 90% of our energy needs. In addition, unlike European countries, we are an island nation, so we do not have access to international power lines. Thus, we have to secure and adjust our own electricity needs. As a result, we have a very vulnerable structure in terms of security. In terms of the power supply structure, thermal power using fossil fuels accounts for over 75% of the power supply, which is considered to be the cause of global warming, and the amount of carbon dioxide emitted when producing a certain amount of electricity is extremely high. In France, nuclear power accounts for about 70%. And if they add so-called stable renewable energy sources such as hydropower, about 80% of the power source is decarbonized. This contributes greatly to both stable supply and CO2 reduction. Japan has a limited amount of time to tackle the extremely difficult task of securing stable, inexpensive energy sources to support daily life and industry without being affected by the situation abroad, while at the same time achieving carbon neutrality. The government's policy on how to position nuclear power toward carbon neutrality is described in the Green Growth Strategy for Carbon Neutrality by 2050, which was presented in June this year. Specifically, as you can see here, nuclear power is capable of supplying large amounts of carbon-free electricity in a stable manner and has the characteristics of high technological self-sufficiency. Technology self-sufficiency means that the country has its own technology to generate energy. This is also a very important point for energy security. Through further innovation, we will achieve further improvements in safety, reliability, and efficiency, as well as reducing the hazardness and volume of radioactive waste, and improve resource recycling through the effective use of resources. In addition, the technology will meet various social needs, such as coexistence with renewable energy, hydrogen production, and heat utilization. In addition, the sixth basic energy plan, which was formulated recently, basically follows the green growth strategy with regard to nuclear power. The plan calls for the development of fast reactors, technological demonstration of small modules, and establishment of elemental technologies for hydrogen production using high-temperature gas-cooled reactors. The next slide summarizes what is required for nuclear innovation towards carbon neutrality, or in other words, what the new reactors to be developed must meet. First of all, we need to improve safety, and this is already a prerequisite for social implementation. In principle, a severe accident such as core meltdown cannot occur, or even if it does occur, it must have such a high level of safety that the evacuation of residents is practically unnecessary. Next, it must be a decarbonized power source that enables stable supply. For Japan, which has few natural resources, it is important to ensure energy security that is not affected by the situation overseas. In order to ensure energy security, it is essential to have energy production technology and a supply chain domestically in Japan. There are 2 points to resource recycling. One is the need for a solution to the finite nature of uranium resources in order to secure energy over the long term. The other is to reduce the environmental impact by recycling the high-level radioactive waste, which is one of the disadvantages of nuclear power. In order to promote the introduction of viable, renewable energy sources such as solar and wind power, it is necessary to provide a system that can absorb daily or seasonal variations. In addition, other than power sources, it should also contribute to reducing CO2 emissions from industrial activities. In order to achieve this, it is also necessary to devise a way to ease the location conditions. The Ministry of Economy, Trade and Industry, the Ministry of Education, Culture, Sport, Science and Technology, and the Japan Atomic Energy Agency, JAEA, are working together to develop NEXIP, an initiative to support the private sector in the development of innovative technologies, from basic research to the development of self-sufficiency technologies. In other words, in other countries as well, innovative development is being promoted with the support of the government. For example, in US, as you can see here, the ARDP, a new type of demonstration program, has been launched in 2020, and support for development is provided according to the maturity of the technology. 2 of the demonstrationable technologies that were selected were the sodium-cooled fast reactor proposed by Terra Power, which was founded by Bill Gates, the founder of Microsoft, and the high-temperature gas-cooled reactor proposed by X Energy. As for the sodium-cooled reactor, a project is underway to build and operate it in Wyoming in the late 2020s. In case of Japan, we are promoting the creation of innovations not only in Japan, but also in cooperation with France and the United States. As I mentioned earlier, JAEA provides support to the private sector for technological development as an innovation hub. Here, I would like to introduce the high-temperature gas-cooled reactor that JAEA is developing as a new type of reactor. I would like to give you a brief overview of this reactor. As the name implies, the gas, helium gas, is used as a coolant, so the outlet temperature can be as high as 900 degrees Celsius, which allows for a variety of heat flows. The fuel is coated particle fuel, which is shaped like a tiny sphere shape with a diameter of less than 1 millimeter, and the nuclear fuel is coated with 3 layers of ceramic, which has been proven to trap radioactive materials even at a high temperature of 1600 degrees Celsius. These coated fuel particles are mixed with graphite to form a fuel compact, which is then placed in a fuel sleeve to form the fuel section, which is then placed in a graphite block to form the core. In the event of an accident, it has an inherent safety feature that reduces the core power. The heat capacity of the graphite blocks that form the core is very large due to the use of helium, which does not transform and has excellent heat resistance. For these reasons, it has high level of safety that prevents core meltdowns from occurring. The next slide shows the potential use of Htgrs. The upper left figure shows the temperature range of various heat values. Down below, right here, I'm showing the temperature range of Htgr, fast reactor, and light water reactor. As you can see, these Htgrs are expected to have a wider range of applications than other type of reactors. The upper right is a hydrogen production. Then there are industrial applications such as supplying heat and electricity to chemical plants instead of fossil fuels, and hybrid systems with renewable energy. This system can absorb variable components by switching to load following or hydrogen production, taking advantage of the functionality of the Htgr. Also, as mentioned here, cogeneration. The cogeneration system is a cascade system that combines multiple applications, and it has a thermal efficiency of 80%, which enables very high level of effective utilization. The high-temperature engineering test reactor, HTTR, which is an experimental reactor as the ORI Research Center, resumed its operation at the end of January this year for the first time in about 10 years after the Nuclear Regulation Authority, NRA, conducted a conformity assessment of the new regulation standards. After resuming operation, we will first conduct safety demonstration tests as an international project of the OECD.
Here, we will look at the safety. Even the core, the pump stopped, which sent a coolant. It will shut down safely. As a part of the technological development in utilization of the heat, in order to establish the technologies to create hydrogen by using HTGR, by 2030, we would like to develop technologies to link HTGR and hydrogen production facility in a safe manner. As a carbon-free hydrogen production technology, we are developing Thermo-Chemical hydrogen production of IS process. Hydrogen can be produced through thermal decomposition of water, but it requires heat above 4,000 degrees Celsius. Using chemical reactions of iodine and sulfur makes it possible to lower the thermal decomposition temperature to 900 degrees Celsius. High temperature heat comes from the HTGR can be utilized. We call this process IS process by combining element symbol of iodine and sulfur. This diagram shows the principle. Basically, input water to cause chemical reaction and then decompose the product with heat to extract hydrogen and oxygen. Both iodine and sulfur circulate on both sides while changing shape. No harmful waste nor CO2 is emitted. At Jaea, as a standalone test before linking it to nuclear reactor, we have achieved of the world's first 150 hours of continuous operation, 30 liters per hour, using the test facility made of practical industrial materials. This fiscal year, we have achieved 92 liters per hour hydrogen production, as well as validation of evaluation method by outputting necessary data. Next is also the introduction of fast reactor technology development we are conducting for achieving nuclear innovation. Combining a fast reactor and cycle, we call it fast reactor cycle. This slide is a summary of its features. First of all, compared to a light water reactor, efficiency of utilization of uranium resources is more than 10 times. The amount of nuclear material present in natural uranium is only 0.7% or so. Fast reactor can convert remaining approximately 99% of resources into new fuel, that is plutonium, to use as fuel. Recycling of spent fuel drastically improves effective use of uranium resources, which means there will be no need for import. Fast reactor is technologically self-sufficient. Domestic production is possible, therefore ensuring stable energy supply without any impact from overseas situation. No CO2 emissions during power operation. Nuclear material called minor actinide becomes high-level waste, but this can be burned. The amount of radioactive waste can be reduced, and the period until the radioactivity decays can be shortened from 100,000 years to 300 years. Earlier, I said plutonium can be produced, but it can also be burned, plutoniums, efficiently, meaning that plutonium management is possible to meet the energy situation. From the viewpoint of flexibility, by combining fast reactor with a thermal storage, it can complement the variable renewables such as solar and wind power. On safety, it has very high safety level due to high natural circulation head. By using air cooler, enable stable decay heat removal for a long period, which will keep the core cooled even in the event of a total blackout, like Fukushima Daiichi. As such, fast reactor cycle has features contribute to realization of innovation required by the green growth strategy. This is Jaea's milestone of FR development and options. Development works will proceed in accordance with a strategic roadmap decided at the Nuclear Ministerial Meeting held in December 2018. Around in mid-21st century, start of operation of fast reactor by a realistic scale at that time is assumed. Various technological innovations are being considered by private sector, universities, and JEA. In the middle of this period, we will look at social needs. For instance, if the priority is on a base load or a power source and it has to be the large reactor, if the priority is on plutonium balance and it's a plutonium burner, if the connection with the renewable is a priority, and then a small modular reactor called SMR. With such options in mind, we are engaged in development works to meet such variety of needs. The role of JEA is to use this strategic roadmap to develop basic technologies and research infrastructure which can meet the needs of various technology developments by the private sector, and establish R&D platform, including R&D infrastructures and knowledge, which have been accumulated through development of sodium-cooled fast reactors. Developing evaluation methods necessary for design, development of codes and standards which reflect international standards, and development of safety enhancement technology for a new type of reactors, which are indispensable for commercialization. We are forging ahead with these activities while capitalizing on international cooperation. We will consider potentiality of various technologies and narrow down the options around the end of 2023 to identify high potential ones. Strengthening cooperation with industry and related ministries to narrow down technologies to promote R&D for the introduction of fast reactors at an appropriate timing in the mid-21st century. I will explain about development of safety enhancement technology and comprehensive evaluation method using next slide. This is one example of a safety enhancement technology, specifically the example of enhanced countermeasures against core disruptive accidents. At the time of a nuclear reactor trouble, basic for secure safety is shutdown, cool, and confinement. This is about shutdown. When there is a trouble in nuclear reactor, in order to stop the nuclear reaction to save the core from disruption, control rod is inserted. It works as a brake. By adding new concept brake to this conventional brake, core disruption can be avoided in a more secured manner. Sorry for the busy slide, but this is what we call self-actuated shutdown system using temperature sensing alloy. Normally, a control rod is hanged with a magnetic power. But at the time of trouble, the temperature of core will rise, and that will push up the temperature of cooling agent. The change is sensed and weakens the magnetic power, which will cause spontaneous insertion of control rods without any human intervention, and it will stop reaction. Even in the case of core meltdown, introducing inner duct structure like this into the fuel assembly to discharge molten fuel spontaneously from the core early to achieve and maintain subcriticality. Such mechanism is developed. Fuel discharge behavior was confirmed by in-pile experiments by Htgrs in Kazakhstan. As a technologies to support innovation in the area of evaluation method and innovative plant design support, we are promoting the development of digital triplet, Arcadia. Arcadia consists of three systems: KMS, knowledge system, consolidating accumulated knowledge and experience of prototype reactor Monju; VLS, analysis system, consolidating simulation technologies; and EAS, evaluation system to identify optimum solution by controlling AI. If we put a plant design into Arcadia, it will optimize it and output optimized design idea. Arcadia makes it possible to optimize design while incorporating various perspectives, which was difficult to do in the past. It reduces design period and cost by substituting large experiments. It innovates the design process of FR and proposes competitive plant concept well accepted by the society. Though through our consolidation of knowledge and technologies, it will contribute to technology transfer and human resource development. My final point is on contribution of FR to the non-energy field, a way to explore potential innovation of FR. What is most promising is production of radioisotope for medical use. Nearly 100% of RI used for cancer test or treatment are imported or difficult to import. From the viewpoint of medical security, domestic production and supply system is strongly needed. In particular, actinium-225 is attracting attention due to its effectiveness in cancer treatment. However, the annual production volume is so small. That is why it is very hard to get it in Japan. It has been even difficult to conduct studies. We found out that actinium can be produced easily if the neutron field of FR is used. We have received requests from multiple academic society in the medical field and patient associations. In order to respond to these needs, we have started R&D activities for production using ORI's test reactor Jaea since last year. This is the summary page. Due to the interest of time, please read them later. This is a URL for our website of the sector of fast reactor and advanced reactor research and development. Please visit this website. Thank you for your attention.
Thank you very much for your kind attention. Next, we would like to move on to the reports made by the young researchers. As for the questions, I would like you to wait until the Q&A session after all the presentations are complete. Now with that, I would like to introduce the first presentation under the title of The Role of the HTTR and the Overview of HTGR. And the presenter is Mr. Nagasumi from the High Temperature Engineering Test and the Research Reactor Department, HTTR Technology Section. This is Nagasumi from the High Temperature Engineering Test and Research Reactor Department. I would like to start my presentation. The introductory part is to talk about the role of the HTTR and the overview of Htgrs, followed by the first topic, the development of a new safety design policy with consideration of inherent safety measures. The second topic is the efforts towards restarting the HTTR operation, and at the end, the future prospects for the commercialization of Htgrs. The Htgr is an innovative nuclear reactor that can contribute to carbon neutrality through its diverse heat utilization and excellent safety features. Research and development is underway in the United States, UK, Poland, and other countries. The lower left shows the difference between LWRs and Htgrs. Compared to LWRs, Htgrs can supply heat at a very high temperature of 900 degrees Celsius, which enables high power generation efficiency. It is also possible to use this high heat for a wide range of thermal applications, such as hydrogen production and seawater desalination. This is the first feature. The second feature is the excellent safety. Htgrs can be designed to prevent core meltdown, as in the case of Fukushima Daiichi nuclear power plant accident, when all power is lost and the core cannot be cooled. This is achieved by using a helium coolant that is stable even at high temperatures, a graphite core with excellent heat resistance, and ceramic-coated fuel particles that can confine radioactive materials even at 1,600 degrees Celsius. Thus, JAEA had set up the HTTR in Oarai, Ibaraki Prefecture, to carry out research and development. The HTTR achieved its first criticality in 1998 and the world's highest reactor outlet temperature of 950 degrees Celsius in 2004. The HTTR has three roles to play in the commercialization of Htgrs. The first is to establish the technical basis for Htgrs by accumulating operational test data. The second is to contribute to the development of safety design policies for commercial Htgrs through safety demonstration tests. The HTTR resumed operation this year, and we are accelerating these activities as we speak. Next, I would like to talk about the first subject, which is the development of new safety design policy that takes into account the inherent safety features. At the time of the construction of the HTTR, the inherent safety features of Htgrs were recognized, but because it was built for the first time in Japan, the safety design policy was based on that of LWRs. For future utilization, it is necessary to establish a new safety design policy that takes into account the inherent safety features of Htgrs. In order to solve this problem, we have developed a new safety design policy based on the safety demonstration tests we've conducted in the past. This safety demonstration test simulates the loss of reactor cooling function by shutting down the gas instantaneous circulation, reducing the coolant flow rate of zero, and not using control rods to shut down. We have demonstrated that the reactor power naturally decreases and stabilizes in this condition, and that the core is naturally cooled by the decay heat radiated from the pressure vessel by heat conduction radiation from the core. Based on these results, we've developed a new safety design policy that takes into account the inherent safety features of Htgrs and have obtained a license from the NRA to change the reactor installation. The specific changes to the safety design policy are summarized in the table here, and the basic safety functions of the reactor, such as shutdown, cooling, confinement, are incorporated with the inherent shutdown characteristics, natural heat radiation from the core, and confinement by coated fuel particles playing their respective roles. As a result, the importance of the existing safety equipment 1 through 5 has been optimized, and the design requirements have been relaxed, so the large-scale reinforcement work to secure the power supply for dynamic components, which is essential for LWRs, is no longer necessary. Next, I will explain the future prospects for the commercialization of Htgrs. We've established a task force in the HTTR department to study the effects of the long-term shutdown, to identify possible obstacles to restart the operation, and to confirm the integrity of the equipment through operations without nuclear heat. We also worked on safety measures to meet the new regulatory standards. Below shows the countermeasure against external fire. We newly constructed a fire break around the HTTR facility. As a countermeasure against internal fire, fireproof and heat shielding barriers have been installed to protect cables. The HTTR resumed operation on July 30 this year. The upper left figure shows one of the items identified by the task force as explained earlier, which is the observation of the thermal displacement of the cooler. As you can see, the past data and the current data are consistent, and we've confirmed that the supporting structures are functioning properly. As you can see, by confirming the concerns at each stage of the output increase, we are able to ensure safe and stable operation. In addition, with the resumption of operation, we've also resumed to accumulate technical information to establish the technical basis for Htgr. Finally, I would like to explain the future prospects for the practicality of Htgrs. What I'm going to show you here is what the Htgr should do for the green growth strategy for carbon neutrality in 2050. The part that is circled in red is what the HTTR be doing during the fourth mid to long-term objectives period. First, we will conduct tests to confirm the inherent safety of the HTTR and to promote international collaboration using the HTTR. We will aim to demonstrate the safety of Htgrs through safety demonstration tests, which are international joint tests conducted by the OECD NEA. As for the development of technology necessary for the hydrogen production, we'll connect hydrogen production facilities to the HTTR and demonstrate the production using nuclear heat. This is a safety demonstration test. The loss of core flow test at 30% power has already completed in FY 2010 and will now conduct the loss of core flow at 100% power. In addition to the loss of core flow at 30% power, we will stop the reactor vessel cooling system, which indirectly cools the pressure vessel to simulate the loss of all AC power and all cooling functions. We will confirm that the reactor can be maintained in a safe state under this condition. Through this test, we'll aim to prove the inherent safety features of the Htgr in actual HTTR and to obtain the necessary data for the development of a commercial reactor. Next, I'll explain the connection between the HTTR and the hydrogen production facility. The overview is shown on top right. The hydrogen production system is installed next to the HTTR and is connected by high-temperature helium piping to produce hydrogen by steam reforming using nuclear heat from HTTR. As shown in the schedule below, the first step is to complete the design of the hydrogen production facility and the connection design and obtain necessary permits, followed by retrofitting, commissioning, and hydrogen production testing. By 2030, we will demonstrate long-term stable hydrogen production using the Htgr and establish the connection technology. Finally, I would like to explain the prospects for the fourth medium to long-term objectives period to promote the technological development of Htgrs that contribute to carbon neutrality. We will establish the technological basis through safety demonstration tests using HTTR and demonstrate Japan's Htgrs through international collaboration, connecting hydrogen production facility to HTTR and demonstrate hydrogen production using nuclear heat. We will continue these activities to achieve the three goals. Thank you very much for your kind attention.
Thank you. Next presentation is geochronological studies of rock samples by a local analysis technology by Yokoyama Tatsunori. Geochronology Research Group, Geoscientific Research Department, Tono Geoscience Center of Jaea. Dr. Yokoyama, please. I'm Yokoyama from Geochronology Research Group. Today I'm going to talk about geochronological studies of rock samples via local analysis techniques. First of all, geosphere stability for long-term isolation of radioactive waste, conducted at the Geoscientific Research Center. The concept of a geological disposal is to isolate high-level radioactive waste generated from the power generation from the human environment by emplacing the waste in a rock deep underground. As you know, Japan sits on top of convergence point of several tectonic plates. As you can see on the right diagram, due to crustal movement and volcanism, when it comes to site selection, measures are taken to select stable bedrock and a region with the least impact of such. In the legal process for selection of the repository site, actual geological survey is conducted at the time of preliminary investigation and detailed investigation. Collected sample is used to evaluate geological stability. Objective of study on long-term geosphere stability is to develop technologies necessary for site disposal designs, safety assessment, and site selection. When it comes to study on long-term geosphere stability, prediction of long-term future is one of the key points. This is to accurately understand the history of geological and natural phenomena to extrapolate past trends into the future. As for tasks in the long-term future, prediction include development of dating techniques for evaluation of recent activity of faults and reduction of uncertainties in understanding of geological events by sophistication of dating methods. This is the overview of Tono Geoscience Center. It is located in Tono area of Gifu Prefecture, consists of Toki Geochronology Research Laboratory and Mizunami Underground Research Laboratory. At Toki Geochronology Research Laboratory, cutting-edge analytical equipment for dating are used to conduct long-term geosphere stability. When we study long-term geosphere stability, we conduct chemical analysis of geological samples to discuss natural phenomena took place in the past. These are the natural phenomena we look for. Geological samples include pyroclastic materials and minerals found in igneous rocks and sedimentary layers. Chemical analysis on these samples is conducted to acquire information such as element concentration and date, and we discuss how and when these rocks and minerals were formed and in what environment. Next, please. Here, I will talk about dating, which is in my presentation title. Radiometric dating is a method used for dating rocks and materials. The method compares the abundance of a naturally occurring radioactive isotope within the materials to the abundance of its decay products, which form at a known constant rate of decay. Easy way to understand is to picture a sand clock. Assume the sand in the upper bulb is a parent nuclide. Over time, the sand will flow down to the lower one. Determining how much sand has flown to the bottom bulb will make it possible to estimate time passage. This is a basic principle of radiometric dating. In this radiometric dating method, mass spectrometry is used at the end to measure radionuclide. Basically, there are two procedures for this analysis. Wet chemistry, the procedure to decompose rocks and minerals with acid, and local analysis using direct laser radiation. Next, please. I mostly use local analysis to analyze rocks and minerals. Laser ablation and inductive coupled plasma mass spectrometry is combined is called LAICP-MS. That is what I use for dating. This photo on the right shows how laser beam is focused on rocks and minerals. Craters is formed like this. Ablated particles in the form of fine particles or aerosol are transported to ICP mass spectrometry on the right and analysis is conducted. Advantage of this analysis is observable direct analysis, simple preparation, large quantity and multi-point measurement, and so on. Next, please. The greatest advantage of local analysis method is the possibility of understanding past geological events in each stage. For example, as you can see on the left diagram, assume there is a mineral with a formation age of 1 MA and growth duration of 0.1 MA. Assuming crystallization starts from the center of the mineral, it is expected that the more center you go, the older it gets, and the more outer you go, the younger it gets. If we use wet chemistry procedure to analyze this, the result obtained is the average age, such as 0.95 MA. In case of a local analysis, information we can obtain is age of 1 MA for center and 0.9 MA for outer area, meaning we can elucidate crystallization growth of each stage. This is a case study using local analysis. This is a joint research conducted by Yamagata University, Earthquake Research Institute of the University of Tokyo, and Gakushuin University. New analytical technique was established by focusing on mineral called zircon. Objective of the research is to evaluate the regional uplift and erosion history of the plutonic rock body by understanding cooling processes of magma, such as the time temperature path of zircon. Zircon is a mineral found in granite and plutonic rocks and is highly resistant to thermal alteration and weathering. Also, as crystallization advances, as you can see on the right-hand side, it is known to present a banded zonal structure. If we can collect the crystallization age and temperature from the individual zone of zircon, we'll be able to characterize the cooling path of rock bodies. Earlier, I said a local analysis to date the mineral will give us information on the left. Center 1 MA, outer zone 0.9 MA. In this research, temperature information is added. Measuring titanium concentration of zircon enables us to know the crystallization temperature of zircon. If we add temperature information to the mineral shown on the previous diagram, as you can see on the right bottom, cooling process of magma has started 1.0 MA and magma experienced cooling of 200 degrees Celsius per 0.1 million years during this zircon growth. There were some cases of determining crystallization temperature of zircon from titanium concentration or determining crystallization age from UPB age in the past. However, analysis was done with different devices or different sample point, meaning simultaneous determination for the single analysis spot was not possible. Concentration level of titanium in zircon is low in many cases. Therefore, there were technical difficulties to analyze low level of titanium concentration. In this research, we have selected analysis device to accurately measure low level of titanium, and by looking into the new analysis condition, we were able to establish new method of simultaneously determining zircon UPB age and titanium concentration for a single pit. This allows us to discuss crystallization of zircon accurately with a high spatial resolution and contributes to the evaluation of a TT path of magma process. As I mentioned before, this technical development will contribute to the reduction of uncertainties for the future predictions. In summary, in Tono Geoscience Center, we perform development of new analytical technologies for dating geological samples to provide scientific information concerning the long-term geosphere stability. Local analysis methods such as LAICP-MS makes it possible to understand past geological events in each stage. We developed an analytical technique for simultaneously determining zircon UPBH and titanium concentration for a single pit on LLICP-MS analysis. Lastly, I would like to touch upon a prospect towards a fourth mid to long-term objectives. In the nuclear energy field, analytical technique for the dating have been developed and demonstrated by Jaea, and it is a fundamental technology for long-term safety assessment of geological disposal and fault investigation of the nuclear facilities. In the area of geological disposal, there is a need for dating covering wide timescale. Capitalize on unique capabilities of Tono Geoscientific Center as a comprehensive dating research center. We will continue to push forward with these R&D activities to lead the world in this field. I may have rushed a little, but this concludes my presentation. Thank you for your attention.
Thank you very much for the kind attention. Next, we would like to move on to the next presentation. The title of the presentation will be The Development of a Computational Method for Elemental Separation that Enables the Design of New Separation Reagents. The presentation will be made by Mr. Masashi Kaneko, research scientist from Radiochemistry Research Group, Nuclear Science Division, Nuclear Science Research Center, Nuclear Science Research Institute. My presentation is titled Development of a Computational Method for Elemental Separation that Enables Design for Novel Separation Reagents. My name is Kaneko. I would like to talk about the title of this presentation, which has to do with separation. Now, first of all, I would like to show you an image of the separation of elements. In this flask, there's water and different elements A and B. One of the most common separation techniques is the solvent extraction method. The solvent extraction is a method of separating elements such as metals by using solvents such as water and oil that do not mix. In this separation method, the metal is dissolved in water and the separating reagent is dissolved in oil. After separation, the metal in the blue circle combines with the separating reagent to form a compound called a complex, and the two metals are separated. This method is used to separate useful metals from the waste of home appliances known as urban mining. In the nuclear field, it is used in reprocessing to extract uranium and plutonium from spent nuclear fuel, and in the separation and transmutation of high-level radioactive liquid waste generated by reprocessing. One of the key technologies in the separation and transmutation technology is the separation of minor actinides and lanthanides, which are known to be very difficult to separate. The reason for this is that the periodic table of elements shows that lanthanides and minor actinides are in a vertical relationship. It is known that it's very difficult to separate elements that are in a vertical relationship. In order to develop this separation, we would have to select the reagent from the catalog and test their separability and repeat trial and error, which is a very time-consuming process. So it was suggested that computational science could be introduced to somehow accelerate the process. As shown in this example, we were able to narrow down the separation reagent selected from a catalog by predicting the separation using a computer. As a result, the number of separation tests can be reduced. It's also been proposed that the feedback can be used to design more efficient separation reagents by improving the separation reagents. In this study, I focused on the separation of minor actinides and lanthanides at the first step to accelerate the development of separation reagents by computational science. The purpose of this study is to develop a computational method to reduce the separation performance and to clarify the principles and causes that determine the separation. A typical calculation or computational method in the field of chemistry is the density functional theory. This method uses the wave equation, which is an equation of quantum mechanics, to solve for electrons in atoms and molecules. And by solving this wave equation, we can analyze the energy of electrons and the shape of orbitals, which are the container of electrons, and evaluate the stability of complexes which are formed by the reaction of metals and separation reagents. The separation factor is actually a measure of how many times the minor actinides can be extracted and separated compared to lanthanides, and is used to calculate the separation factor. In this computational method, when a metal reacts with a separation reagent to form a complex, the energy of the reaction can be calculated for lanthanides and minor actinides, and the difference of the stability of the complex can be used to estimate the separation factor.
Conventional density functional theory set by default was used for calculation of 5 reagent cases. The vertical axis represents experimental values and horizontal axis represents calculation values. This is the result. Underestimate. Calculation value underestimate vis-a-vis experimental value. It is difficult to predict separation performance. The problem is a conventional method does not reproduce separation factor. And tuning DFT method is necessary. Then we focus on a chemical bond. Ionic bond and a covalent bond are a representative bond of chemical. Ionic bond can be seen in salt, that is the electrostatic attraction between oppositely charged ions. Covalent bonding is the sharing of electron pairs between atoms. Chemical bonding between metal and reagent in complex present characteristics of both ionic bonding and covalent bonding. It is expressed as a mixture of ionic bonding and covalent bond characteristics. However, interaction and chemical bonding in Ma and Ln, the complex is complex and not well known. What I have done is to determine the optimum ratio for Ma and Ln complexes by mixing covalent bond to ionic bond. Conventionally, values such as 0 and 20% were used, but we have determined that 50% being optimum. We have re-estimated separation factor by changing the ionic and covalent ratio to 50%. As a result, we were able to reproduce SFMALN. Learning here is covalency is important for MALN separation. Therefore, we decided to conduct analysis on separation mechanism by carrying out analysis focusing on covalency. This is the molecular structure of complex with high separation agent, TPEM. As you can see, metal is present in the middle, and reagent is surrounding the metal. Covalent bond is ultimately important when we focus on orbital overlap or fluctuation of electrons. This is the structure of complex described with orbital overlap. Ma complex is on the left and Ln complex on the right. In case of Ma complex, overlap between Ma and reagent is very large, meaning strong covalent bond and a stable complex. On the other hand, Ln complex orbital overlap is small, therefore low stability. We found out that strongness of orbital overlap is origin of separation mechanism. As a result, in order to control complex stability, it is necessary to control covalent bond. This is the summary slide. DFT method is applied to reproduce Ma-Ln separation performance. Elucidate the separation mechanism based on covalency. We were successful in designing and prediction of novel reagent based upon the mechanism by improving conventional reagent with the aid of computational science. This is only a calculation value. However, we will conduct synthesizing reagent and separation test. This is prospect towards the fourth mid to long-term objectives. We would like to engage in development of separation reagent by introducing computational science and AI. As a new challenge, we would like to pursue applicability of element separation in other scientific fields, such as element separation for production of medical RI or rare metal recovery. This concludes my presentation. Thank you for your attention. Thank you. We now would like to start Q&A session. As a countermeasure for COVID-19, we would like to ask those of you who would like to ask a question to come to the microphone in the middle of the hall. Also, please state your name before asking question. Thank you. In order to offer everyone an opportunity to ask a question within the limited time available, we would like to limit questions to one per person. Also, it will be helpful if you could identify specific speaker and section of the presentation that your question is for. For those who are joining us online, please send your questions to the email address dedicated to this session. Let's start with the audience here. Please raise your hand if you have any question to any of the four speakers. Anyone? If not, I would like to read one of the questions we have received online. This is for Dr. Oshima. What are the advantages of high-temperature gas reactor compared to light water reactor in terms of contributions to carbon neutrality? 50% better? I would like to have a quantitative answer. I'm Oshima. It is a very difficult question. Quantitative answer is quite difficult. Both have pros and cons. In particular, in case of Htgr, as I mentioned earlier, a very high temperature is useful for heat usage rather than power generation. Replacing fossil fuel, which are used to generate heat at factories, or produce hydrogen for hydrogen car will contribute to reducing CO2 emission in transport sector. Wide area of applications like these are the benefit of Htgr. From the perspective of power generation, temperature and thermal efficiency are good. What remains is the cost. Htgr is still in a process of development, so concrete comparison is difficult for now. It is not quantitative, but rather qualitative, but HTGR is versatile and has distinct characteristics of a high temperature. It can be applied in various fields. That is the advantage.
Thank you very much. Any other questions from the floor? Please raise your hand if you have any. If not, I would like to entertain another question that were posed through online. This is a question to Mr. Nagasumi. I have heard that the research on gas reactors has been stopped overseas, and why is that? I'm Nagasumi. Thank you very much for your question. Globally, the research and development has been carried out on an experimental basis since 1960, and effective results were obtained there. However, the Chernobyl nuclear power plant accident triggered a change in social conditions and a decline in demand for nuclear power, so research and development has been suspended. However, the safety in nuclear reactors has been greatly improved, and the demand for nuclear reactors is increasing in order to realize a decarbonized society. So the research and development is being promoted again. Thank you very much. Please. Can you show me the slide? Do you think you can show my slide? I would like to add to the earlier answer. I happen to have a slide that summarizes how the current FBRs are being promoted around the world. Here it is. As you can see in the figure, various countries are considering various types of HTGRs. Thus, the research has not been stopped, as this reference shows. Thank you very much. If you have any other questions from the floor, please raise your hands. No questions? Please. On to your right, there I see one hand up. So I would appreciate it if you can walk towards the microphone to ask your question. My name is Morimoto. I'm a general participant here. I would like to ask you about HTTR. When is this planned to be in practical use here in Japan? Can you explain, please? Thank you for the question. Since the question is regarding HTTR, Mr. Nagasumi, please respond. Thank you very much. Can you show my slide? I would like to use this slide to explain. By 2030, we will establish the technology necessary for carbon-free hydrogen production and establish technological foundation through safety demonstration tests. Then, starting in 2040, we will conduct demonstration tests using the IS process and HTGR to demonstrate the scale necessary for commercialization. After that, we aim to commercialize the technology in the 2040s. That's it. Thank you.
Thank you. Are there any other questions from the floor? If not, I would like to read a question we have received online. This is for Dr. Kaneko. What type of computer do you use for simulation? Personal computer or supercomputer? Thank you for the question. We use Workstation, which our research group owns, and also Jaea's large computer for calculation. Thank you. Are there any other questions from the floor? If not, I would read a question sent online. This is for Dr. Yokoyama. Could you tell us the reason why you are conducting research in Tono district? Thank you for your question. I'm Yokoyama. Could you show my presentation slide, please? Tono Geoscience Center has Toki Geochronology Research Laboratory and Mizunami Underground Research Laboratory. Tono mine used to be located here. To secure nuclear fuel for a nuclear fuel corporation, research lab was built here. That is a historical background. The name was changed to Toki Geochronology Research Laboratory, and it is now conducting R&D on geological disposition. I don't know if this answered the question, but this is why we are conducting geochronological studies in this area of Gifu Prefecture.
Thank you very much. If you have any other questions, please. No questions? If not, I would like to read the question sent through online. Question to Mr. Kaneko. The development utilizing the density method for the separation reagent, how are you incorporating the radiation field impact into your computation? Thank you very much for the question. In the calculation that I'm conducted, I am not able to take into account the effects of radiation. However, in the future, I would like to consider reactions such as the decomposition of separation reagents due to radiation and incorporate factors that inhibit the decomposed separation reagents into the calculations. Thank you very much for such a important question. Thank you very much. Any other questions from the floor? Again, I would like to entertain another question from online. This is a question to Mr. Nagasumi. I heard that the core of the Htgr does not melt, but even if the fuel and structures are safe, isn't there a risk that the control rods and internal components will melt? What is the heat resistance of those pieces? Thank you very much for the question. Please take a look at the slide. It's been proven that graphite and fuel, which have excellent heat resistance, do not melt, and the control rods and the pressure vessel also do not melt, because the heat is dissipated by heat conduction from the pressure vessel and by radiation. Thank you very much.
Are there any questions? If not, I would like to read a question sent in online. This is for Dr. Yokoyama. In geological disposal, I think what is more important is how a geological layer will change over time rather than how they were formed. Could you tell me how your research results can contribute to geological disposal? Thank you for your question. A very good question. Could you show my presentation slide, please? As I mentioned before, when it comes to study on long-term geosphere stability, we need to predict future natural events. Stability in case of geological disposal does not mean no movement at all. Rather, what is more important is to understand the trend of movement and evaluate the extent of movement. Geochronology, technological development we conduct for dating geological samples is research to determine what kind of geological events took place in the past, for how long, and what changes are brought about. As you said, we also think how it will move in the future is much more important. Thank you. It's time for us to end the Q&A session.
Okay, now it's time. We would like to resume our session. From now, we will go into a talk session. The title is New Nuclear Power and Infinity, and we're still using only a part of potential of nuclear energy. The moderator for this session will be Akira Yamaguchi, Professor of the Department of Nuclear Engineering, Graduate School of Engineering, University of Tokyo. The participants of this session will be as follows. Dr. Reiko Kanda, Deputy Director of Research Institute of Radiation Medicine, National Institutes for Quantum Science and Technology. Dr. Aiko Nagamatsu, Senior Manager of Space Environment Planning, Research Unit 1, Research and Development Department, Japan Aerospace Exploration Agency, JAXA. And from JAEA, President Mr. Hiroyuki Oigawa. Please take the floor. Good afternoon, everyone. I am given the role of the moderator for this session. My name is Yamaguchi from University of Tokyo. We have such a wonderful guests here on stage. I would like to do my best to extract their experiences and their wisdom during the session. Now today, we will be talking under the theme of new nuclear power and infinity, which is Shin atomic energy and infinity. We're still using only part of the potential of nuclear energy. We have various experiences who's here up on stage, and I would like to start from asking every one of you to give a brief self-introduction. Now, starting from myself, I am teaching at the Department of Nuclear Engineering at the University of Tokyo. And since June this year, I've been the president of the Atomic Energy Society of Japan, and I'm also responsible for coordinating the various activities of the society. As you can see on the slide, I majored in nuclear engineering in 1984 as a doctoral student at the University of Tokyo. And then I joined the ORE Engineering Center of the Power Reactor and Nuclear Fuel Development Corp, where I was mainly engaged in research related to fast reactors. In the first talk today, Mr. Nagasumi talked about the HTTR and said that safety test of Htgrs would be conducted as part of an OECD project. I also remembered that around the same time, there were safety tests of fast reactors such as FFTF and EBR-2 in the United States, and that fast reactors were said to be very safe and can be safely shut down without scramming. And I was reminded of this story as I was listening to Mr. Nagasumi's talk. Now, at the Power Reactor and Nuclear Fuel Development Corp, PNC, which is the current JAEA, in 2005, I moved over to Osaka University. And in Osaka University, there was a new major called Environment and in Energy Engineering. And so I went to the university since the inception of that new major course and had studied together with the students who majored in environment, energy, nuclear power. And from 2015, I moved to University of Tokyo. As is indicated here, my profession is nuclear engineering and safety engineering and risk studies. After Fukushima Daiichi nuclear power plant accident, we have come to a conclusion that Japan should have done a better risk assessment. And there is a PISM, which is an international society, and I became a member of that society in order to work towards working on safety aspect for the nuclear energy. So as this represents, I myself has been immersed into nuclear power since then. Now with that, I would like to pass the microphone over to Dr. Kanda. Thank you very much. My name is Kanda from National Institutes for Quantum Science and Technology, QST. In 1990, I received my PhD in the field of fish hormones and later joined the National Institute of Radiological Sciences, in short, NIRS, which is sometimes referred to as NIRS as short, and I've been conducting research on radiation protection for the past 30 years. The NIRS was merged with part of the former JAEA to form the National Institutes for Quantum Science and Technology, QST, in 2016, of which I'm currently the Deputy Director of NIRS, which is responsible for research and operations related to radiation protection and exposure medicine. I also serve as the Director of the Research Department, which conducts research on radiation protection. In terms of my research expertise, I've been working on radiation dosimetry and risk perception among Japanese people since I joined NIRS. Both seems like a different research field, but they're important from the standpoint of radiation protection. And in 1999, when the Criticality accident occurred in Tokai village, I developed a dosimetry method using chromosome aberration indices to assess the doses of severely exposed patients. And nearly 20 years or so have passed since then, and the method I've developed at the time has become recognized as the standard method internationally. As for the other research, the risk perception survey, when the nuclear accident occurred in Fukushima, we had the opportunity to explain to many people about radiation and its effects. And it became the basis for such explanations and the development of tools. In addition to my research activities, I've been involved in the formation of a network of medical radiation associations and a network of radiation protection societies for the past several years. To give you an example of what this network has been used for, the academic societies have worked together to determine reference values for radiation doses to be used in radiological examinations. This will help reduce unnecessary radiation exposure to patients. These are some of the activities we're doing to help the society. I'm looking forward for today's talk. Thank you very much for that. Next, Dr. Nagamatsu from JAXA, please. Thank you very much. People participating online and people here in this room, good afternoon. My name is Aiko Nagamatsu, and I work at the Research and Development Department of JAXA. I belong to a team that develops detectors for measuring space radiation, magnetic field, electric charges, and space debris from satellites flying in low Earth orbit to geostationary orbit, and also develops and operates and analyzes data for detectors that measure radiation environments on the International Space Station and radiation doses of astronaut biological samples. Our group conducts various missions to study space radiation measurement and shielding protection for international space exploration. In February next year, the first rocket of NASA's New Space Launch System, the successor to the Space Shuttle, will be launched to carry international space exploration. This first rocket will launch a micro-satellite called Omotenashi, which was developed by JAXA. There's a micro-satellite called D-Space that's going to be launched, and it's going to be the mission to measure the radiation levels. And as you can see, in February next year, the first rocket of NASA, the New Space Launch System, will be explored. But in September 2024, we will launch the MMX Mars Satellite Mission, which is a mission to observe the Martian satellite Phobos and Deimos, as you can see in the top figure. In September 2024, the MMX mission will be launched from the Tanegashima Space Center by Japan's new H3 rocket. This mission carries IREM, Interplanetary Radiation Environment Monitor. This IREM is an energy spectrometer that measures the energy spectrum of solar flares. Our dosimeter will also be installed in the NASA-led gateway to the near moon, which is scheduled to be built after 2025. Our mission is to apply the results of our space experiments to the shielding protection research and design for the next generation missions. Thank you. Thank you very much. Now, I would like to ask the president of JEA, Mr. Oigawa, please. I'm Oigawa from JAEA. I am currently a member of the board executive directors, but I also serve as a department head of the Nuclear Science Research Department and the Safety, Research and Disaster Prevention Support Department. I was a researcher in the field of reactor physics, which is more of an engineering field. And I studied how neutrons behave in nuclear reactors. When I was doing this research, I used a device called the Criticality experiment device, which is a reactor with an output of a few watts, about 9 orders of magnitude lower than a normal reactor. Even so, because it was a nuclear reactor, we were able to simulate the physical phenomena and nuclear reactions that occurred in it, and use that to conduct experiments. As an extension of that, I moved on to researching the possibility of applying neutrons to the nuclear transformation of long-lived radioactive nuclides. At that time, the construction of J-Park was underway and planned to conduct nuclear transformation experiments there. Since then, I moved on to management, and now I am in charge of planning the overall R&D of JAEA and promoting basic research on nuclear energy prior to the current position. So nice to see you, everyone.
Thank you for the self-introduction. Let us begin the talk session. So the keyword is new era nuclear science and technology. What kind of image that every one of you have? For instance, We just heard three participants introducing themselves. They are engaged in nuclear power, but there is many aspects that can be expanded into the new field. Potentialities of the future dreams. Well, I hope today's talk session will give you opportunities to think about it in a more concrete way. First of all, Dr. Kodama talked about radiation therapy earlier. And so he talked about the Jaea's 2050 plus. In there, and this new era nuclear is not just means a new type of nuclear power. The radiation is something that is close to everyone's daily lives. And so a nuclear power in a context of a society. So you can see a nuclear in different perspectives and how that will shape a nuclear. And so those are the things we would like to think about in this talk session. Without further ado, I'd like to ask Dr. Kanda. And Dr. Kanda was talked about radiation therapy. I think radiation therapy is a very useful technology and receives a lot of attention from the society. So I would like you to talk about this more, especially compared to nuclear power. Radiation has many challenges closely related to the people's daily life. You have touched some of those. Such things may come up more in a society going forward. Well, you have been focusing on both radiation measurement and risk awareness. I think nuclear technology will be used more in medical fields and to improve quality of life. There are many aspects to think about, such as technology, society, and psychology. First, I would like to hear your opinion and perspective based upon all the studies you have conducted so far. Yes, Professor Yamaguchi, thank you. I think there was the key word that is close to people's daily lives. In radiation therapy, it is clear who receives benefits and who faces risks. In that sense, it is really close to people's daily lives. How it is perceived in a society is something that we are always mindful of. Technology, psychology was also mentioned as a keyword. It has its own challenges, I think. First, I'd like to talk about psychological aspect. When we conduct risk awareness survey, radiological test is scary is some of the typical answer given by a large number of people. And they also say they want to avoid taking it if possible. But when we ask detailed follow-up questions to such respondents, we often find out that they were not categorically denying radiation. Rather, they are relatively tolerant with radiation therapy if it's the matter of life and death. But like cancer treatment or the test for the heart disease or brain. On the other hand, many people said that they did not want to go through dental x-rays to check a cavity or check bones, which are more commonly used. How can we interpret this? People are not judging radiology tests just by their fear for radiation, nor radiation dose. Rather, they are making a rational decision based upon benefits. That is how it's perceived now. If I may talk about technological challenges with this psychological aspect in mind, it will drill down to how to maximize the benefit of radiation therapy while minimizing risks. Let me talk about some of the research conducted at QST. A heavy particle beam therapy is a therapy to kill cancer cells located deeply under the skin by using carbon Japan has been leading the world in technology development. We are in a process of developing next generation treatment facility called quantum scalpel. It uses multi-ion irradiation, which combine carbon, oxygen, and helium ions to make the treatment more effective with few side effects. However, this will not work on very small metastatic cancer. Therefore, targeted radioisotope therapy, that is to bind radionuclide to a very small cancer cell, is concurrently used to increase the benefits and reduce the risks. This development is still ongoing. Unfortunately, it is not possible to reduce the exposure to normal tissues to zero yet. In other words, the risk of developing cancer a few or decades after treatment, so-called secondary cancer, is not zero. In the past, it was okay if it cured cancer. Also, most of the patients receiving such treatment were seniors. However, nowadays, even children go through radiation therapy, meaning that hospitals should properly understand radiation dose used in a treatment to control the risk of secondary cancer. By doing so, psychological challenges can be addressed. Did I answer your question, Professor Yamaguchi? Yes, thank you. You said it is important to properly measure radiation dose to determine exposure level and also know the benefits. Knowing the level of exposure makes it possible to compare risks against the benefit, but it also gives patients more sense of relief, I assume. Thank you for that. I'd like to ask Dr. Nagamatsu next. Dr. Kanda just talked about radiation therapy using quantum scalpel cannot reduce the impact of radiation to zero. That is why proper measurement of radiation dose is important. I think there are some similarities between space and nuclear fields. They are both very challenging and technology-rich. In space, of course, there are cosmic rays. So, space development and radiation are inseparable. When it comes to space, many people associate it with dreams and expectations. Well, it may be the case that ordinary people are not well aware of or do not care about cosmic rays so much, I wonder. Dr. Nagamatsu, you have talked about small dosimeter developed in Japan being used on board the spacecraft. Protecting astronauts will be very important when we think about the time when people are going to be more active in space in the future. I heard that the Martian moon's exploration mission will start soon. We often see astronauts working in space, such as astronaut Noguchi conducting experiments in space. I assume some astronauts may have concern about radiation control. Could you talk a little bit about it with some examples? Yes. Astronauts, first, last week on November 9th, mission crew Akihiko Hoshide of JAXA returned safely to the Earth after staying on board the ISS for 199 days. While on board the ISS, he was wearing personal dosimetry called crew padless. We will be analyzing the data for now, including 11 Japanese astronauts. The number of people who have been to the space so far is only approximately 600 in total. This year is said to be the beginning of a commercial space flight here. 2 U.S. companies succeeded in suborbital flights in July. Mission to go on a suborbital flight of 100 kilometers in altitude to experience weightlessness for a few minutes. And in September, a Crew Dragon, a new type of spacecraft of SpaceX, succeeded in a mission of orbit around the Earth with all civilian crews. A trip to the moon, a week-long mission to the moon with hundreds of crews, are also planned in the future. Many more people will have a chance to go to space. Not just astronauts, but if you was to go to space, you may feel cosmic rays more relevant. I have talked with the astronauts on the topic of cosmic rays before. Some of them highlighted the topic of informed consent, saying that they received information on potential risks of cosmic rays exposure in space before the mission. Some highlighted onboard experience of setting and operating our dosimeter made them more interested in cosmic rays and collected academic paper on cosmic rays measurement after returning to the Earth. While staying in the ISS, some astronauts experience seeing flashes called light flashes or astronaut's eye. That is caused by charged particles going to retina. Those who pursue advancement of space development, like myself, knows cosmic rays are something that cannot be avoided in space. But they're also posed as challenges and restrictions for advancement. Things such as satellites, parts, and materials for a device which go on board the shuttle must go through some form of test or evaluation to check resistance against cosmic rays so that we can reflect the result in selection and design. Also, National Institute of Radiological Science, the institute Dr. Kanda works at has a HIMAC. Together with the Jaea, the JPAC accelerator, we must conduct evaluation tests in line with our mission to confirm before the launch. Cosmic rays are part of background radiation, which exists all the time, but there are also challenges we must overcome. That is why I see them very close. Thank you, Dr. Nagamatsu. What is impressive is that you are very well aware of the existence of radiation as something very close to our daily lives. That is why you see the need of a proper management of radiation. You also pointed out the importance of being able to measure the radiation. It was interesting to hear that you have used various facilities such as JPARC to conduct evaluation. Later, I would like to hear more about the cases where some astronauts, after having experience in space, engage in various other activities. I was happy to hear about it as a person work in science and technology field because I see the opportunities of collaborations. Now, Dr. Oigawa, both Dr. Kanda and Dr. Nagamatsu talked about using Jaea developed technologies and collaborations in their respective field of medicine and space development. Jaea is Japan's sole comprehensive nuclear research and development institution. We often associate Jaea with a fast reactor, gas reactor, or reprocessing. How do you see this new era nuclear, Dr. Oigawa? If you think about needs in medicine and space development, this new era nuclear could expand in multiple directions. How do you or JEA think about this?
Now, when it comes to new era atomic energy or Shin atomic energy is concerned, it is quite difficult to define this, but I think there are two ways to think of. In order to promote the utilization of the atomic energy, one of the importance is safety, and then the other is waste. The two would have to be solved in order to elevate this atomic energy into a next level, which I think is quite important as part of new era atomic energy is concerned. Being said that, when it comes to atomic energy, as was mentioned earlier, radiation, or even if it's not radiation, nucleus, or using something at the same level with the atomic energy can maybe be extracted from some world which is not familiar to us, like micro or nano level of the world. And if you're able to do so, I would say that the Shin atomic energy or new era atomic energy would have all kinds of ways for application use. In the world of medicine, for example, quantum scalpel, or say targeted RI therapies, or Dr. Nagamatsu had mentioned about the exposure in space or shielding seems to have been one of the very important factors. And JAEA has a computation structure called FITS. Especially in the aircraft operation, there are often cases where the solar flare and the space, the cosmic ray peaks out. And we've developed the system to be able to predict that peak. And also, in terms of collaboration with QST, one is the RI development. JRR3 had started its operation this year, so the RI is developed. And as the President, Mr. Oshima, had mentioned in his presentation, once this becomes part of a regular operation, then this could be put into the second development for each of the teams. And I think that this could maybe be able to be utilized more and more in the field of medicine. So the technology owned by JAEA would be able to be utilized in various fields of technology, which I think is quite important. Yes, thank you very much. When the general people heard of nuclear power, people tend to feel scary. But as Mr. Oigawa had mentioned, I think this has to do with the quantum beam, meaning it's not visible, it's microscopic, therefore it's quite difficult to image what this is all about. However, as Dr. Nagamatsu had mentioned, the experience by the astronauts, I think, is quite interesting. I think it's quite interesting to hear the stories from astronauts themselves. And I was wondering whether the astronauts are talking about their own stories at the lecture sessions. Do you know of that? Thank you. Once astronauts are done with his or her mission, they would share such experience in the field of education or science and conduct lectures. And I would say that this kind of topic is part of such talk that individual astronauts are speaking in public. So then in that sense, people who are currently engaged in space research and development, not only from the standpoint of sharing the experience such as astronauts are doing, but I think that JAEA has one of the top-notch facilities that can be of a pride of Japan and also being renowned globally. So I think that the communication there would be able to be instrumental in terms of space medicine. When it comes to know-hows, facilities, or human resources that JAEA has, I think is quite important. And I think that we would be able to expect highly of utilizing those people, because not only people, but knowledge, experience, and the facilities of JAEAs are quite important for us to think of how we can utilize this Shin atomic energy concept. And I think the president of JAEA, Mr. Kodama, had also spoke about 22050 plus. And I think this is going to become the trigger to further discuss what we can do in that 2050 plus scheme. Now, from the standpoint of Dr. Kanda or Dr. Nagamatsu, I would like to hear from both of you as to how you feel about this. Dr. Nagamatsu had earlier mentioned about the joint research in terms of fits. And I think you have a direct communication with JAEA yourself. So I would like to hear from you as to whether you have any requests towards JAEA or any impressions that you had as you worked with JAEA people. Thank you. Now, when it comes to predictive measurement technology that supports atomic energy, this is also a core in terms of space development as well. Not just exposure dose or exposure to the astronauts, but this is going to be quite instrumental in terms of design and also the detectors that would be mounted to the spacecraft. We have done a joint research to date, but when it comes to the experimental module of Kibo, there is a fit simulation code computation results that replicate this Kibo quite well. And at the same time, there is a PADLIS, which is a monitoring measuring system. And both data would be able to be analyzed and compared so that we can decide and see what kind of shielding effect that this International Space Station has. So the FITS not only does the computational analysis, but the process and the people who went through the process of FITS would have the knowledge who could become quite helpful in the exploration of international space. Thank you very much. Maybe the developer of FITS would be able to become the person who could fly in the space aircraft. Yes, that could be possible. It's interesting. And I think the person could develop and fly and then come back and do the analysis, him or herself. Well, that would be interesting. The young people from JAEA can maybe think of doing that yourself. In the world of medicine, especially in the medical field, sometimes when the radiation therapy is concerned, the exposure would become quite important. Sometimes the irradiation would have to take place at a specific lesion in quite an accuracy. But, people are not always still, so I'm sure it's quite difficult to do that. Now, Dr. Kanda, talking about the human resources of JAEA and facilities, we've kind of talked about the RI manufacturing, which has more to do from the standpoint of the nuclear reactor. But from the field of medicine, is there anything that you would like to say towards JAEA? Now, in QST, we have the research department who does the research on quantum beams or nuclear fusion. But those were part of JAEA, therefore, I'm sure they're doing the joint research in that field. But from the medicine standpoint of NIRS, especially in the field of dose assessment using FITS, is one of the most project that's been promoted jointly with JAEA. And this is also the great interest by the ICRP as well. In the past, we would normally set the dosage to a standard person, and then based on that information, radiation protection system were developed. However, today, it has become more specific, such as race, age group, or individuals it's themselves, and therefore the dosage evaluation and the risk evaluation has become so personal. And I have mentioned earlier that there must be a well control to be done for the secondary cancer risks. And this is going to be helpful in order to explain to the patients of what's happening. And I think that it is the source of trust from the patients as well. Especially in the last year or two, the patient who went through the heavy particle radiotherapy, we already knew how much of the exposure to the lesion of the patients, but we are jointly developed the system in order to understand the extension of exposure. The question is, how could we be able to utilize that system? I think that this can be incorporated into the therapy plan, treatment plan of patients who's going through the cancer treatment. And at the same time, we could be more specific in terms of amount of exposure dose from the past treatment of the patient from epidemiological standpoint. So understanding the risk could be further promoted. So from that sense, we would like to work together with JAEA's technology and also people so that we would be able to make sure that the dose evaluation would be able to be done in a more and more accurate manner. Thank you very much. When there is a computational tool like FITS, I think that this radiotherapy could become more of a personal-made system. As I was listening to what you say, the computational technology have advanced, therefore the FITS was able to be developed. FITS has a very renowned codes that's been cited often, and I think that this is a great achievement by JAEA. In the presentation, Mr. Kaneko had mentioned in the presentation of the density functional computational theory to optimize the separation coefficient. I think that this is something that he said that he's going to work with the experiment side. And I think that this is also going to help develop the personified RT radiotherapy amongst patients. I think that this kind of computational codes or simulation is currently underway because there are quite a number of examples already. But I think that the people's wisdom from JEA and the software can further be utilized. And I think that is the essence of innovation or open innovation in a way. And I think this is the way to go forward. Now, as Mr. Oigawa has mentioned, in terms of, say, capacity building or computational codes, facilities, there are various requests that people are expecting towards JAEA. I would like to now hear from the president of JEA, Mr. Oigawa, to share with us of what you have in mind as you've listened to all those voices. Well, many of you had mentioned about FITS quite often, and I was quite amazed to hear that there were so many users existed. When it comes to the FITS, this was actually developed in order to understand the shielding capability of developing accelerators. But today, this is used in medicine, space, and soft-Htgrs. And I think that as this computational science develops, I think the simulation activity would become quite promoted. The strength of JAEA is that JAEA has the accelerator. And also, in terms of the world of chemistry, JAEA owns a facility that can use the radioactive substances, meaning that there is a certain organization that can do the validation, not just computational code alone. As Dr. Yamaguchi had mentioned, FITS has various collaboration expected from different fields. So I think that we are currently in the position in which we could further seek for such collaboration. So we would like to place importance on such collaborations with other fields. the current atomic energy is more mission-oriented, or it's more like project-based kind of approach. But as Dr. Yamaguchi had mentioned, facility and also human resources are still abundant other than those usage. Therefore, we should change our mindset so that we can seek for the collaboration going forward.
Very important perspectives are being shared now. Hearing new era nuclear as a keyword, first thing came to my mind was using nuclear energy not only in power generation but in other energy fields and usage of radiation. As Dr. Oigawa said now, one interesting way to pursue this new era nuclear is to put nuclear facility, HR, software together as a comprehensive set to go into the new field. This cross-sector collaboration does not always work, but I hope that Jaea can capitalize on their people, facilities, and knowledge to show us examples of how drastically better the result could be. When it comes to nuclear, as it was mentioned already, and in similar to space and medicine, but from the viewpoint of a nuclear engineer like myself, nuclear power generation and nuclear energy are not seen as something so relevant to daily lives, but this is not the case. Actually, a radiation reactor has many aspects which can be applied in industries, therefore promising. There are many ways to contribute to society and industry in Japan. Society 5.0 and the sixth industry, such new terms being used to question how society in the future should be, being sustainable in a decarbonized society, making lives of people in Japan more affluent, adapting to fit the new era of society. With this in mind, we can be more creative in shaping the future of nuclear. Dr. Kanda and Dr. Nagamatsu, what do you think of new era can bring to Japan and the world? I know this is a difficult question, but could you share your thoughts? Maybe first, Dr. Kanda. Yes, I'd like to speak based upon my expertise, that is radiation protection. New era nuclear, if technology is to be developed with a close link with society, what is indispensable is radiation protection and understanding of general public. When I explain about radiation, I often say you cannot see or feel radiation, but you can measure radiation. So proper management will be the key. Well, we can only measure radiation point by point. But if we could visualize radiation, it makes it easy to protect and conduct new era nuclear science and technology in various fields. Fortunately, the dosimeter cost around 10,000 yen is sufficient to measure air dose rate, gathering a large amount of big data combined with the Jaea's excellent technologies, I think will make it possible to visualize radiation of places. Well, in the area of medicine, doctors who perform IVR sometimes being exposed to a large amount of radiation because we do not know the source of radiation or area of high dose. We are now developing a device that can visualize high air dose area by overlaying real world with data. To me, visualizing radiation is like adding odor to city gas. If it becomes possible to sense or see radiation, radiation protection becomes more real to everyone. This is not the innovation for the sake of innovation, but for the people. It will be a useful technology for those who support nuclear. Thank you. Well, if we combine technologies such as digital twin or big data, real space can be seen more closer. Thus, risks can be better managed and treatment outcomes could be improved. That was a very inspiring point. Dr. Nagamatsu, I heard that you have analyzed a sample brought back by spacecraft Hayabusa. In the area of the materials and technology for analysis, in relations to space, are there any expectations for the future? Yes, from the viewpoint of space development, I'm interested in J-PARC, Japan Proton Accelerator Research Complex. As you mentioned before, in December 2020, the asteroid explorer Hayabusa 2 successfully brought back samples such as sand and rocks from the asteroid Ryugu. Elemental composition analysis of these samples were conducted by using J-PARC's Material and Life Science Experimental Facility, MUOM. As I said before, MMX, a Martian Moon exploration mission scheduled in 2024, is also a sample return mission. Not just JAXA, but other countries are planning a sample return mission for international exploration. There will be a heightened need for elemental composition analysis in space development field. The cosmic rays are radiation with a wide range of energy originated from galactic cosmic rays and some protons. The area relevance to exposure dose is quite wide-ranging from MAPE to JEV order. Therefore, dynamic range evaluation is necessary. It is necessary to evaluate high-energy secondary particle, a neutron beam, originated from primary cosmic rays, but there are only few places in the world which can do this. Is the challenge. J-PARC can extract the highest energy photon in Japan. Diversification of evaluation capabilities and further sophistication is what I expect for J-PARC. Thank you. You're right. Space exploration, such as Mars, will require analysis of minute materials. Dr. Yokoyama, I believe, talked about laser ablation in his presentation today. We understand the deployment of nuclear and radiation measurement technologies in medical and space. Dr. Oigawa pointed out safety being the important challenge for the future. And President Kodama and Dr. Oshima also mentioned decarbonization under the basic energy plant and contributions to carbon neutral. New era nuclear should have a role to play in these energy issues. During the Q&A session, and Dr. Oshima talked about the value of Htgr and various fields. It can be used. I do have high hope for this. How JAEA can contribute to solve various issues and increase value of nuclear towards a carbon neutral. Could you share your thought? Yes. Our policy is to do everything we can. First, Dr. Kanda's suggestion of visualization of radiation. Actually, Fukushima division is working on the system development to visualize the status of contamination inside Fukushima Daiichi in 3D format. It should not be too far before we will be able to apply it in medical field. To the Professor Yamaguchi's point, nuclear energy, the mainstream. As I said before, safety level must be high to be accepted here in Japan. We will continue to propose high safety. In the sector of nuclear safety research and emergency preparedness, which I'm responsible for, optimization of emergency preparedness and residence evacuations are also being considered. When exposure is not so high, unnecessary evacuation should be avoided. We should be proposing ways to make quantitative comparison of risks possible. Using nuclear energy not just for power generation but for hydrogen production is something that we should be exploring. Reducing volume of waste is something we must do. When it comes to nuclear, we must clear safety and waste issues. Otherwise, it will be difficult to further develop. A topic of analysis was mentioned, and also the J Park is mentioned. In the Hyogo Prefecture, we have beamline called Spring 8. Radioactive materials can be used there. Various analysis and analysis on samples brought from Fukushima is also possible there. We would like to come up with the technology which treat waste more rationally. Another thing we want to do is a bit beyond the concept of nuclear. Atom and atomic nuclei has a character called spin. Using this spin, what we called spintronics, not electronics, but spintronics, system that can transfer information without applying electric current, developing device with extremely low power consumption. There is some of the idea for the nuclear application. The seeds for challenges are everywhere. What is important is not just looking inside our organization, but to look into other fields for collaboration. Thank you. Direction, such as energy, radiation, and in addition to that, what all combined? Social infrastructure. Now it can be said that the nuclear is a part of social system. I started to see many potential directions you can pursue. The contents of new era nuclear are yet to be seen, but I have so much expectations. We are running out of time, but I would like to ask Dr. Kanda and Dr. Nagamatsu, who offered us inspiring opinions today, to share their feedback on today's session and expectations they have, positive or not, for JEA.
Starting from you, Dr. Kanda. Well, when I first accepted this offer, I heard the keyword of new atomic energy or new nuclear or shin atomic energy. And I've asked the question as to what this specifically meant. I received a lot of materials from JAEA, and this actually written various technological seeds, and there were a lot of information that could be spun off and be able to be applicated into various other areas. But if in case this came along as a coincidence of a crossover, I felt that this outcome could now be able to make into a necessity, so that various fields would be able to leverage this particular collaboration. And I hope that this would further be promoted, and I'm looking forward to see some of the events that have been hosted by JAEA. Well, you know, one of the downside of JAEA is to send such tons of information over to you. But thank you for sharing your request towards JAEA as well. How about you, Dr. Nagamatsu? Well, I have heard the young researchers' presentations, and I went to the materials that were laid out on the foyer outside of this room, and I come to see that there were a lot of common technologies of space development and risk aversions that JAEA has been developing in the field of safety management and prevention of disasters. So there are a lot of information that we just simply not know, but could be of an importance to the space development. Our location is in the same prefecture because our Tsukuba Space Center is only an hour drive. And it's very close to J Park or Tokaimura, and therefore I think that this kind of collaboration can further be promoted. Thank you very much. As myself being a moderator for this talk session, I would like to also summarize the talk. Well, the nuclear power has been developed thus far, and it was solely for the sake of power generation. But when it comes to this new era, nuclear energy is concerned, I think that this is not only separate ourselves from the rest of the utilization. I think that it is important that we look at this in a comprehensive manner, and not just to improve people's life levels or quality of life. I think that the technology should be utilized in the society as well. And I think that this nuclear energy has a potential to be able to exhaust such capabilities. Now, when it comes to atomic energy, in terms of peaceful usage, this goes back to 1953, Atom for Peace by President Eisenhower. And in Japan, in 1955, there was Atomic Energy Fundamentals Act were set forth in order to secure energy source by use of nuclear power. But since then, there are a lot of technologies that had advanced in the industry levels. But we are only 60 years or so since its inception of nuclear power. Therefore, we would be able to further seek for the technological development. And I think that we were able to see more potential of utilization of the technology. Dr. Kanda, Dr. Nagamatsu had shared with us on the possible collaboration in the field of medicine and space. And I think that there could be more further effect that we would be able to seek by collaboration. It's a JAEA-hosted symposium, but I'm hoping that this atomic energy would be able to be utilized in different fields so that not only the energy issue, but I'm hoping that this would be further presented into the different technological field so that this would benefit people's lives or welfare of people, so that people would be able to understand that JAEA's technology is very much usable in the real world. And with that, I would like to summarize this session. Thank you all very much. Panelists, thank you all very much for your kind cooperation. Dr. Yamaguchi, Dr. Kanda, Dr. Nagamatsu, thank you very much. Please give a big round of applause to them.
登壇者の皆様におかれましてはご移動の方よろしくお願いいたします。それでは本日のプログラムの最後といたしまして、
The last agenda item on today's schedule. Mr. Ito Yoichi, Executive Vice President of JAEA, I'd like to invite Ito to offer closing remarks. I'm Ito, Executive Vice President of JAEA. Thank you very much for staying with us for such a long time today. This year's symposium was held hybrid with live audience and online audience. We have received over 105 non-JAEA participants and around 500 online participants. In addition to those who came to join us here at the hall, we were able to receive online participants who live far away. We were very happy that we were able to share the result of research result of JAEA. We have a special homepage for this symposium, and there is a link to a survey. We hope you can share your frank comments. And today, we have heard from young engineers and researchers about their research result. Through today's presentation, I hope you'll be able to feel what they're doing is relevant to you. During the talk session, we have heard frank comment being shared in terms of a new era, a potential nuclear, and expectation for JAEA. I thank you for all the frank comments and suggestions. With this precious comment in mind, we would like to continue our determinations to pursue our mission as a Japan's sole comprehensive R&D facility in nuclear. With this, I would like to end my closing remarks. Thank you very much for your participation and attention. With this, we would like to close 16th Annual Symposium of the JAEA's activities. When you leave this hall, in order to avoid congestion, I would like to request you to leave this hall in accordance with the block you are in. Our staff will give you instructions, so please follow our staff's instruction. There is a survey form available on our website. Among those who have filled out a survey, we will be sending our original novelty goods. November 24th, Wednesday, is the deadline, 10 a.m. Thank you for your cooperation. For those who are with us here, you can find a survey sheet in the package that you have received today. We will be collecting a survey sheet on your way out. For those who have filled out the survey, we will be offering you the novelty goods. A video will be posted on our website at a later date. Everyone, thank you very much for joining us for 16th Annual Symposium of Jaea's activities today. All the audience here with us and all the audience joining online, once again, thank you very much. Please take all of your belongings with you when you leave the hall.